All right. Hello, everyone. I'm Diana Gray, and it has been my honor to serve as the president and CEO of the Hydrocephalus Association for nearly 10 years. Can you believe that, Asim? Almost 10 years. Thank you for joining us. You are here because you're an important group of people who join us in being highly invested in our HA mission of finding a cure for hydrocephalus and improving the lives of those impacted by the condition. Essentially, you're our VIPs, and we are extraordinarily grateful for you. This briefing is our opportunity to provide an exclusive forum to highlight the impact of our mission work. So I'm going to share just a bit about our organizational health and successes, as well as a few concerns that are weighing on us. And then you'll also hear from two impressive scientists, as well as our new board chair, Stephanie Vogt, shortly. So let's get started. Let's start with our support and education update, because that's what we were founded on, is doing amazing support and education. Our programs continue to grow and evolve, and in 2024, we had an incredible HA Connect National Conference in Tampa with nearly 600 in attendance. And as always, this event provides an opportunity to learn from leading experts and foster connections with others who share lived experiences with hydrocephalus. We received so many positive comments from participants about the sessions and their overall experience. A conference of this magnitude, though, doesn't happen without the support of our very generous sponsors. And if there are any of you on, thank you, and an impressive faculty. So thank you to our presenters at the conference as well. But we also have some exciting news, because we've never been able to firm up our new conference location this early. So we're excited to have confirmed our HA Connect 2026 will be in Indianapolis, thanks to presenting sponsors Riley Children's Health and Indiana University in Indianapolis. And we have Dr. Bonnie Blazer Yost to thank for being really instrumental in advocating for this support. In fact, if you come, we're going to do some lab tours with her lab. So we'll be hosting in Indy July 23rd through 25th and 26th. So mark your calendars. And if you forget, it's on our website. We have a new research-informed program for parents who often experience post-traumatic stress related to the surgeries and challenges their children face. It's called RAISE, R-A-I-S-E, and it helps to build the skills of resilience. So check that out on our website if you want to learn more, but it's a really beautiful program. We are incredibly excited about another new program we are about to pilot for the newly diagnosed, called the Next Steps Kit. This kit includes an adorable bear with a shunt, along with other resources. The bear is named My Hydro Bear, with hopes that the children will name their bears what they want to name their bear. And we really hope this will connect families to HA earlier than ever before. So let's talk a little bit about our advocacy efforts. So in 2024, it soared to new heights, with the Congressional Pediatric and Adult Hydrocephalus Caucus growing to its largest size ever, with 39 members. 39 members. If we get 4 more, we'll be a 10% representative caucus of Congress. So we're really excited to keep growing that. And now more than ever, you need to have a powerful caucus. So it's been a busy time for our advocacy team, and your voices have amplified the call for more funding, awareness, and policy changes to improve the lives of those affected by hydrocephalus. So since launching our research program in 2009, the Hydrocephalus Association has significantly advanced the field of hydrocephalus research, investing $16.4 million to date. And actually in 2025, we're on track to invest another $700,000 in grants this year. This investment has generated an impressive $91 million in additional funding, with our supported scientists and clinical networks securing grants from the NIH, Department of Defense, and other foundations. So together with our investment and what these scientists have secured after our investment, we've infused $107 million into hydrocephalus research. So terribly excited about this, and we want to continue to see this happen. In 2024, we achieved a milestone by awarding a record number of research grants, underscoring our unwavering commitment to driving innovation, expanding the research ecosystem, and advancing progress for the hydrocephalus community. So How many was it? Our awards total in 2024 was 24. 12 awards included Innovator Awards and Accelerator Awards and Engineering Student Awards. We've been doing these engineering roadshows across the country to incentivize engineering students to help us create new and better solutions. Cool, right? Let's get them while they're young and have them help us solve this problem. The other 12 awards were travel awards for young scientists to attend our conference and present their research. Another way to hook students, give them that opportunity. We continue to host high impact research workshops annually and could not do this without the generous support of the Rudy Schulte Research Institute. Our upcoming workshop will focus on the engineering challenges of treating hydrocephalus effectively. You know, HA raises nearly all of the funds for our programs from scratch every year, which is why your continued support is so valued. Our walk leaders are rock stars as they led 42 walks across the country, bringing together more than 6,000 participants across more than 785 teams. In total, our walks raised over $1.8 million. So I know we have walkers on this call. We adore you. Thank you so much. And thank you to our walk donors who are on this call. We adore you as well. We're thrilled to announce that in 2025, 2 more new sites will happen in Huntsville, Alabama, and one in the Central Valley of California around the Stockton-Modesto area. Within our walk success story is a brand new collaboration with Wingstop locations in Utah. If you haven't had Wingstop, you need to go. Wingstop locations in Utah, spearheaded by the Garin family and their Hydro Warrior Peyton. And they've expressed interest in expanding this opportunity this year. So expanding beyond Utah, that would be amazing for the Hydrocephalus Association and our mission. Okay, so that's the good stuff. Let's talk a little bit about, what's keeping us up at night. Frankly, we're deeply concerned about the cuts to the National Institutes of Health and the congressionally directed medical research program research funding, along with many other research entities like AHRQ and the CDC. Overall, the CDMRP was cut 57% from 1.5 billion in 2024 to now this year 650 million for this year. But within that CDMRP funding, hydrocephalus is considered in one of the categories called the PRMRP category, and that funding is down to $150 million from $370 million last year. And along with us, there are 56 health conditions in this same area for this peer-reviewed medical research program category. So we're competing for less than half of the funding that was available last year. There's news reporting about reducing the 27 NIH institutes into 8. I'm sure you've heard about that. So naturally, it causes concern about the focus hydrocephalus research will receive. So we're hopeful, but worried. We're also learning there's a high probability that NIH will be reduced even further in 2026, potentially by 44%, from $47 billion to $27 billion. The last time the NIH budget was this small was in 2003. So we know the NIH is the world's leading entity and funder of biomedical research. This will be challenging for health conditions seeking better treatments and cures. And sadly, there are already reports of scientists planning to leave the US. In the end, this means less biomedical research funding across the board, and scientists with innovative hydrocephalus research will be vying for a much smaller pool of money. And we're going to keep doing our part to fund scientists, but we need that leader in the NIH. We're very proud that our medical advisory board and our scientific advisory board jointly responded with a statement regarding the importance of biomedical research and why reasonable indirect costs are integral to a lab's ability to operate. Smaller labs would close if they didn't have some indirect funding for their labs. So finally, we're worried about the economy and how even the perception, just talking about a recession, could impact giving, particularly walk donors, and in some cases, our larger donors may feel more protective of resources as well. Simply put, We're juggling many balls currently, but we're trying to remain optimistic with our mission and strategic goals top of mind. So thank you so much for your continued support. And I'm going to introduce Stephanie Vogt, who is our board chair, and she joined the board in July 2022, and she's been a tremendous asset to our organization. So Stephanie, take it away.
Oh, well, thank you, Diana. That was very kind. Thank you. I'm so excited to be here today. And I just want to take a moment and introduce myself, which I look around and I know very many of you, but for those who I do not know, I want to share just a bit of my story. So, as Diana said, I am extremely beyond honored to be the chair of the Hydrocephalus Association board. It has been a dream of mine since I was ever so little. I also chair the St. Louis Walk, and it's been an amazing and very learning experience year after year, but couldn't do it without all of the HA support. So I live in St. Louis. When I was 6 weeks old, I was diagnosed with hydrocephalus. It was later found to be due to aqueductal stenosis. And then fast forward 2.5 years, my sister, who is 1 year older than me, so she was at 4 years old at this point, was diagnosed with hydrocephalus as well due to aqueductal stenosis. So both Sarah and I have what anyone would consider very normal lives, playing with friends, going to school, not a lot of worries as kids, I would say. I'm sure my mom would state this quite differently. But the best part of our years when we look back and we talk about it is truly going to HA conferences. Good heavens, we loved these conferences and getting to meet other people with hydrocephalus, because in St. Louis we did, but honestly, there weren't any our age. So it was very different. I also remember helping my mom fold pamphlets I think it was probably every quarter. I feel like we did it all the time for her St. Louis support group for the Hydrocephalus Association, because back in the 80s, there wasn't a ton of support, right? There's no Google. So she would put us to work when she would come home with these Kinko's maybe copies for us to fold. My sister and I have had quite a different experience with hydrocephalus. I've had just 3 malfunctions in my life, and I am 43. And my sister at age 44, she has had 32 malfunctions. But knock on wood, she has been now 20 years brain surgery free. So, so thankful for that. During one of her surgeries when she was age 14, there were complications and it led to a brain herniation. So she needed to, she was paralyzed on the right-hand side and had to learn how to walk and talk again. Those were tough times. Dr. Walker was a saving grace during those times. In Salt Lake City, they would fly to see him. But she has overcome so much since then and has received 3 college degrees, now nannies and volunteers with any of her free time. So I work full time. I work in the pharmacy benefit industry. I've worked in this industry for about 15 years now, and I am married with 3 very energetic children that keep me very busy. So it's a little bit about myself. And so I just want to take a moment to just be thankful for the time we have together here. We are here to hear from 2 MDs who are conducting some amazing work for hydrocephalus. Research, as you know, everyone knows, right? You guys can all say this. It's so important. It gives us that promise for better treatments for the 1 million Americans plus living with hydrocephalus, and of all ages, right? So one of the things I repeat that I steal from my mom, sometimes I give her credit for saying it, but is that she said this many years ago, and now that I'm a mom, it really hits home. Her goal is that no mom ever has to hear your child has hydrocephalus. And so I stand behind that now that I have kids. Oh, I did not intend to cry. So this research is so important. Some of it going on right now is even going to help prevent hydrocephalus, which I don't know. I don't think that 20 years ago we were thinking that way. We were thinking of how do we find a cure, not going back to prevention. I could be very wrong there, but the various avenues that people are now thinking of and going down, it's unreal. It's amazing. That ROI, as Diana mentioned, it continues to grow. The researchers we fund go on to get incredible follow-up funding from organizations like the NIH and the Department of Defense. But as we know, all of this funding, we have to keep running with it because it's a bit of it's going to be quite at risk here. So I'm so excited about how far we have come and incredibly hopeful for the future for all of us who are impacted by hydrocephalus, and all of the moms and all of the dads and all of the doctors and everyone who is supporting us. So thank you. Thank you all for being such a big part of HA's efforts, for all of your support. And please continue, please keep expanding our reach. So thank you, Diana.
Thank you, Stephanie, for that beautiful talk. Thank you so much. So we're delighted to have two exceptional presenters, both physician scientists and neurosurgeons who care for hydrocephalus patients. So first up is Dr. Peter Chiarelli with Children's Hospital Los Angeles, who was also a 2024 Innovator Awardee. He's an attending physician in the Division of Neurosurgery, as well as an assistant professor of clinical neurological surgery with Keck School of Medicine of USC. Dr. Chiarelli's project is entitled Quantitative Non-Invasive Shunt Flow Measurement for Improved Management of Shunted Hydrocephalus. So Dr. Chiarelli, welcome and thank you for presenting your work.
Thank you for having me. Let's see if my screen share works. Now at Pro, it's screen sharing.
Perfect.
Can you guys see the screen there?
Yes.
Okay. Let me see if I can enlarge my audience view momentarily. Here we go. So I have been a scientist before I did my medical training and continued being a scientist afterwards. I remember what it was like in my life to be a scientist, turning the wheels of science, publishing papers, but not necessarily knowing what impact the science is actually going to have on the real world. This was something that I essentially made a concrete decision to change when I became a clinician, because we only live once, and I think it's really important to put our scientific impact towards problems that exist in the real world. And in the world of neurosurgery, hydrocephalus by the numbers is the most substantial portion of what we do in terms of life-saving procedures and making kids' lives both livable and also better. That said, all of our work here in this collaborative that we build at CHLA is centered around actual problem solving. It's not just about spinning the wheels of science, about solving problems that exist now. And so certain parts of our work have been focused on developing tools to actually understand real concrete things about hydrocephalus, which for some reason have not existed in the world up to this point to a similar extent. So let's talk a little bit about shunt flow imaging. If I can, hold on, if I can change my slide. All right, can you guys see the next slide? All right. So I'll talk a little bit about the goals of our work, our mission, show you what our group looks like approximately. Then I'll kind of tell you a little bit about the clinical relevance. Why is this actually important for medicine and for treating kids and families who have shunted hydrocephalus? And then a little bit about the work that we're doing right now and where we're going, and some cases where it's been actually clinically impactful and has actually changed management now. In terms of science, the idea of doing translational work, scientific work that actually matters in the clinic, is sort of this like shining star ahead of all of us. This work that we've done that I'm going to show you has actually had clinical impact from a period of 6 months between when we designed the work and when it's been sort of implemented in a patient care setting. So it's actually very, very exciting. So I don't need to tell anybody in the audience what hydrocephalus is. We know that it's an imbalance between absorption and production of cerebrospinal fluid. We know that shunts are common, and we know that shunts have been tough to manage for as long as shunts have been invented, essentially. And I'm kind of counting this from around 1952, when the silastic parts from airplane manufacturing in World War II became repurposed, and we were able to produce soft, flexible materials for VP shunt design in their modern form. So our group that we built, the CSF Flow Dynamics Group at CHLA, soon to include Barrow Neurological Institute and Phoenix Children's Hospital, because it turns out I'm actually making a life transition, and I accepted a position as a physician scientist role at Phoenix Children's Hospital. We are planning to expand our group into a 2-institution single group between CHLA, where I'll be remaining adjunct professor, and Phoenix Children's Hospital, where I'll be based primarily, having basically staff and students at both institutions working all together and meeting together. Our goal is to identify technologies which basically should have already been in common neurosurgical practice. The science tends to move faster than the clinical use of the science. And from my perspective, having come from scientific work in material science and a PhD in MRI physics, something felt a little bit off, that there have been techniques that have already existed to measure flow inside small spaces. But from a clinical perspective, this wasn't used in management or investigation of shunted hydrocephalus. And so our initial goal was real implementation of things which should already be useful, just haven't. Basically, the two sides of the two sides of the issue weren't talking to one another. In doing so, we have a way of better understanding the brain's fluid physiology, and we've essentially opened up a new field of investigation, hydrocephalus physiology, which isn't yet in textbooks because there wasn't a tool to investigate it in real kids, real patients. This is a picture of our group. You can see multiple members spanning different areas of the hospital. We have students, nurses in the group, collaborating faculty from emergency medicine, ophthalmology, all across the board. Our students have gone on to medical school now. One is at medical school at USC Caltech. Another one is at Stanford, who just graduated. So excellent group. This was one of our first papers that we published in mid-2024, just really revealing this technique to the world. And essentially, what the technique was using an MRI technology, which I'll explain in a second, to watch fluid move in small tubes. And that sounds pretty darn straightforward and simple. This 1-minute method essentially was so straightforward to perform that it became incorporated in all routine scans that have been done now at our hospital over the last year. So anytime a child gets surveillance imaging who has a shunt, this scan is performed. We've witnessed it influencing shunt management for the better. And by getting this information, we're all of a sudden now exposing a new world of questions that can be answered. These black box questions like, does my child shunt have too much or too little flow? Is there a possibility that that's happening? Does my child still need their shunt? A question that comes up so often, but essentially the only answer to ever have given was kind of a very vague hand-waving type answer. Is there a shunt problem, maybe a partial obstruction that's affecting quality of life? Children with ongoing cyclic vomiting or chronic headaches. Unanswerable questions like this, including how do we modify shunt design to actually make it better in the future, become questions that you could tackle with concrete approaches towards investigation and engineering. And so since we've been disclosing this to the world for the last year that this is successful, there's been interest in basically all the main children's hospitals across the country that they want this too. And that's the whole point. This is the point is to give it to everyone free, to let everyone use it. We're essentially not developing a product for sale. This is part of a scan that kids already get for routine surveillance imaging. Integrating a new protocol does not cost money. It's just to make the scans that we already get way better by providing a new piece of information. And in a plumbing device that sends fluid from one place to another, the idea that we've been existing as a field without knowing how much is actually going through it on a routine basis seems a little bit like, why? And my answer is, I guess just because we haven't, but now we can. So with that in mind, the existing ways that we look at shunts, right? We get clinical histories and exams. We get pictures to see if the fluid chambers are bigger, although we know that in a pretty substantial set of kids, the fluid chambers don't change size when kids have shunt failure episodes. We can do poke needles into the shunts, which is obviously invasive. We can perform these nuclear medicine scans showing radio tracer moving from one compartment to another that, although is appropriate clinical practice, is still a nuclear radioactive material injected into kids. Hopefully our modality will make that as obsolete as a pneumoencephalogram sometime in the near future. And then advanced technologies, meaning things for sale that hospitals can buy, things like wearable sensors and other things to look at CSF flow. I think that this is a very valuable component of the future of hydrocephalus, understanding flow, no matter what the way. I think that it just basically, it all agrees with the idea that knowing the flow inside shunts is very, very important. And so what I'm about to tell you works synergistically with these other technologies. It's not that these are competing with one another, it's that flow is actually important in these systems. So the technology that we started with, the MRI scanning technique that I based this new version of scan on that we developed, was phase contrast, which has been around for a very long time. It's been around since the early 90s. It was developed and it's used very commonly as a cardiac output measure for kids with cardiac conditions. It's also the basis of a very poor scan to look at CSF flow in a Chiari malformation, something that you can do better with, to be honest. But it's a pretty tried and true technique that has been used for other purposes. And what we did was we modified the technique, and we developed a scan sequence that could look at flow in tiny little tubes. And you see an example of how small a shunt tube looks like on the bottom right side of the screen. And to test this, we built a phantom. We basically put a bottle of water and we had a shunt tube running through it, and we drove the fluid at different pump rates to match physiologic rates. And in doing this with real hardware, but just in a water bottle, shockingly enough, we found very reliable results. Not just that in this water bottle, we were able to calculate flow in versus flow out, but that with these representative pictures you can see at different flow rates, you can actually physically see the flow inside the tube. And you could actually build a little laminar flow profile of this flowing liquid in the tube from one wall to the other wall. So it was better than even my radiology and physicist colleagues had expected. I'm going to bypass a few slides that I would normally show because of time, but essentially we tested this in kids, and this non-ionizing radiation, non-invasive, 1 minute long test that is part of a scan kids already would get, turned out that when we tested it in kids who we knew exactly how much is coming out of the shunt because they were externalized at the clavicle for completely other reasons, found out that the amount that we were testing, the calculated amount, exactly matched how much was really coming out. This was not a surprise to us, but it was good for proof of principle. Moving forward from there, we investigated, and this was part of that paper I showed you, we investigated our first 20 patients, showing all the data, keeping everything completely visible for sort of the readership and the people who are trying to interpret this scan. And it found that in these 20 patients, we were able to really precisely calculate the amount of cerebrospinal fluid flow moving through the shunt. And to date, because this was so popular at our institution, we've now collected over 700 values, flow values through kids with shunts, opening up basically a new world to understand shunted hydrocephalus, which just didn't exist before this. For example, I'm showing you a piece of data that was not available to the world before this. In a population of kids with shunted hydrocephalus, what is the average rate of fluid moving through the shunts? We would expect it would be different for different kids because they have different shunts, different valve settings, they are different size, weight, they have different etiologies of hydrocephalus. But these histograms that you're seeing of the most common flow rate of kids with hydrocephalus is just physically new information about shunted hydrocephalus, which was not testable. It was not available before this. And using this information, I mean, there's a whole world that you could use this type of data as a baseline for. This is the type of thing that we're able to find concrete, real pieces of new info. This is an example of a scatter plot. Every dot is a different child, and every child has a different flow. And if you were to ask a neurosurgeon before this, how does the CSF flow change with age? You might get an answer, oh yeah, well, as kids grow, they're probably producing more CSF. You expect that. Turns out that is actually not the case. And I'm highly suspicious that kids produce a different amount, a growing amount of CSF between birth and when they're about 6 months old. But most of this data was acquired so far after 6 months. That's a topic for investigation in the future in young, sweet babies. But it turns out that this relationship is actually, that we believed to be true all these years, doesn't hold in reality. This is something which was, for me, probably the most earth-shattering. This was the first 11 kids who we scanned who, during times of normalcy, not during a shunt revision, received the scan more than one time. And the time between the two scans could be separated by a variable amount of time. So in the little red bars here, you see that some kids were separated by a couple months, some up to a year, for example, patient number 2. But in each case, the flow we measured at the 2 different times was really, really similar. And we plotted flow number 1 versus flow number 2, despite the amount of time interval, on these plots here, these linear plots. And you can see an implication from this, which kind of changes the field a little bit, in that if there are patient-specific flows through a shunt, meaning the flow doesn't bop around every time you check it, if a patient has a certain amount of flow through a certain shunt system that their brain is basically adapted to and is their new kind of homeostasis level, it's their normal, then we can use a known patient's baseline to turn shunt management into patient-centered care. Meaning, this is not a cookie cutter approach. I wouldn't know what your flow would be unless I knew you specifically and what your flow liked to be. But if we know a baseline for you, all of a sudden, the amount of information we can have to assess a shunt, it changes completely because we can base it on your known baseline, and we can make observations and we can make clinical decisions if that flow goes up or down over time. So that, in terms of turning shunt management into patient-centered care, is a pretty darn big deal. And I'll show you in a couple minutes how that has changed a few things. So this is a technique that we're aiming to translate to all scanners and all hospitals. In doing so, part of our investigation, and this has been supported by the Hydrocephalus Association through our Innovator Grant, is to find the best modeling methods. The best way, is there an even better way of calculating flow through this tiny, tiny little tube than just taking an average of the flow inside the tube? So here you can see some MATLAB graphics of different modeling methods for finding the flow. And here you can see some data, which we are pretty close to publishing, again, supported by Hydrocephalus Association, that using refinement of techniques for estimating flow, we're actually able to find different pitfalls by investigating these different scanners, different hardware, coil design, field strength. We're able to actually predict different pitfalls that different scanners would contribute, and we can avoid them. So we've actually been able to make the technique applicable to all scanners that we've come across by this investigation. So meaning everybody can end up using this scan no matter where you are. So taking that and moving on just a little bit, our next plan, and we have these experiments basically just about to be up and running at this moment, is to investigate questions about kids' own physiology who have shunts. So unanswered questions. So the idea is that we have kids living their lives, and a lot of things happen to kids while they're just alive, right? Kids are drinking different amounts of water. They are a different amount of obesity, perhaps, like abdominal girth, that can affect shunt flow. Kids have different cardiac issues. They're exercising. They have cardiac output changes. They might be either taking a medicine or doing something in their life that changes cerebral blood flow. There was just a recent study published that caffeine, believe it or not, affects CSF production. They have different amounts of venous return. All of these are basic physiological variables that have never, in the history of medical science, been investigated in hydrocephalus in an actual population of patients. Now that we have a method to test kids that's safe, repeatable, and doesn't require a lot of angst, this is something where we can manipulate physiological variables for kids and families who are interested to participate, of which we've recruited many from our clinics. And they go through a few little modules. They either chug a bunch of water. We can actually manipulate cerebral blood flow by breathing different air mixtures. They can raise their legs up. They can pedal on an ergometer inside the MRI scan. We can investigate anything and everything that could potentially change cerebrospinal fluid flow, and then know how it's affecting shunted kids. So this is an experiment that's upcoming, and the data on that, I think, promises to be pretty exciting. But it's also a way to investigate future factors that we're not even including in this experiment. So I think a lot of this is, I just kind of said it before the slide was up, but it's a platform for investigating questions in the future, including such trivial things as how does body position affect shunt flow? The number of times that families or individuals, adults with hydrocephalus, have asked the question, could I possibly be overdraining? Is that contributing to my headaches? How much is shunt flow different when I'm standing up versus sitting down? Why are these headaches happening? These are things we can investigate. We can investigate standing versus sitting MRIs in open access MRI centers. And I mean, again, the sort of number of questions that we can answer and the way that we can improve hydrocephalus is sort of an open field. At the same time, there is another method that, do you mind answering this real quick? There's another method that we developed in the meantime so that families can physically see the flow through their child's shunt. This is with another method that MRI method developed at CHLA, believe it or not, 20 years ago, called timestamp, that has not been published until this little paper here that's coming out next week. Nobody thought to publish it, but it's a remarkably better way of looking at cerebrospinal fluid flow. Here's a pulse sequence diagram for those of you guys who are MRI physics nerds like myself. But based on that, essentially, we are magnetically labeling a plane of cerebrospinal fluid. That's the yellow arrows pointing upwards. And the shunt tube is the gray rectangle going downwards. And out of that magnetic, non-invasive, non-radiation label, essentially, the moving spins show up as bright. And doing that, this is some of our data. Again, this is unpublished, so you guys are seeing this before the world sees it. We found that this new method, these line graphs here, show that it basically predicts, it shows the same flow as the old method. except it all of a sudden lets you visualize the flow differently. It's another method, so it actually sort of corroboratively supports the other method. If you have two and you're concerned about one method being wrong, two is better than one. But I'm going to blow up some of these figures here just so that you can see them a little bit bigger on your screen. This picture off here to the left is physically watching the fluid moving inside a shunt. And for a family who has questions, the amount of support that might help provide for understanding what the care exists at that moment, that could be pretty, dramatic. For clinicians to be able to see this, I think that would be equally important. And we can get quantitative data like this line graph off to the middle and the right, where you're actually visualizing flow in 3 dimensions or 2D dimensions as a line graph. This is that same modality, but we've expanded it to actually with patients. So these are 4 kids looking at their shunt flow measured with technique number 1 that was earlier in the talk, and technique number 2, which is called timestamp, and it works. So lastly, I'm finishing up here. What about symptomatic patients? This data, this was never intended to be for clinical use. We were collecting data, and occasionally there would be a patient where I would ask one of my research students, my research staff, hey, could you tell me what the flow is for that patient? I'm curious about something. For patient number 1 here in A, off to the left, this is a patient who just had a scan done before a surgery that they already needed and afterwards. And you can see the flow dramatically improve. That's pretty much expected, but it's interesting to see. Patient number 2 had 2-sided shunts. They had a shunt on their left and a shunt on their right. The clinicians couldn't figure out which side was the blocked one. This graph here, if you put it together from their asymptomatic times and their symptomatic time, you can pretty obviously tell which shunt was the working one before the surgery. And it actually caused a clinical change in clinical decision-making where the correct surgery was done instead of the incorrect surgery. So this graph here avoided a child of surgery. The third graph here, this was a patient who just happened to have received data during a happy time in their life. They came to my clinic with something that didn't quite add up. And there wasn't a scan that showed that there was a problem. But I asked my research team, same thing, hey, what was their flow? And because we found that there was this change based on their known individual specific patient baseline, it caused me to get an x-ray. I wouldn't have done this otherwise. No clinician would have had a reason to do this otherwise. And because I got this x-ray, I found that their shunt was completely broken, meaning that they had a flowing tract despite having their tube fully in their abdomen. It had coiled and plopped down in their belly. And this child 100% would have come to the emergency department in a certain state of disarray any number of weeks or months later. And we basically avoided them that emergency circumstance because we were able to catch this early and operate on it probably months before it turned into an emergency. I'll skip the 4th case, but basically these are all cases of clinical utility. So the whole point here is matching simple technological solutions with real clinical problems that exist now, integrating the findings into clinical practice specifically for the benefit of patients. And because we have this tool, we are exposing a new field of physiology that can be safely investigated without hurting kids for the benefit of having a better understanding about hydrocephalus, better patient care. And from our experience so far, families have been super supportive. They really want to know more about their own kids' hydrocephalus. And so it's been sort of beneficial overall. Thank you guys very much.
Thank you so much, Dr. Chiarelli. This is amazing. We know that you have kids waiting on you right now. You're in clinic. So what I'm going to ask our audience to do is make sure you get those questions in the chat or Q&A, and we will get those answers for you from Dr. Chiarelli and send those out. So unless you want to keep kids waiting, I think we need to let you go.
Okay, I will run. I'm sorry for going over time by a few minutes.
Thank you. No problem at all. Thank you, Peter. We really appreciate you. This is
Bye, guys. Nice to see you all.
All right. Wow. Super exciting. And we have another amazing scientist to talk with you as well, and that's Dr. Cameron Sadegh, assistant professor with UC Davis Medical Center. He was also one of our Innovator Awardees last year for his project utilizing neurosurgical specimens to study intraventricular hemorrhage and the feasibility of targeted gene therapy. His project was one of the projects that was supported by our friends at Team Hydro. So Dr. Sadegh, please, thank you for joining us. Share with us now. Thank you.
Yeah, thanks for having me. Can you guys see my screen okay? I don't know if I have it swapped one way or another.
It's
Um,
good. Perfect.
Yes, we're good.
all right. Um, but yeah, I mean, first off, sorry Peter had to jump off, but I was going to say I want to join his institute. Why not? Make collaborations, work across universities. But yeah, my name is Cameron Sadegh, and I'm really honored to be here and also to be funded by your amazing team group, and I hope I can be part of this for the foreseeable future in many different ways, as a scientist, as a clinician, as a friend. So happy to share my other thoughts on other things that in the future. This is just a picture of my clinical team. You guys all know Dr. Edwards, or hopefully many of you do on the right side. Um, he's not actively practicing right now, but he's obviously a strong part of our team, and you know, he's always a presence. So I have him included on this picture, and then the main picture in the middle is our active pediatric neurosurgery team. The green circles are the surgeons, and then we have the rest of our nurse practitioners and physician assistants. And then I have Jim Bogan on the far other side, who is no longer practicing, but he also was one of our pediatric neurosurgeons. So I'm just thrilled to say I have an amazing group of colleagues, and we're doing a lot of things that are exciting on the clinical end of things, including advanced techniques with flexible endoscopy, um, using lasers in our endoscopic cases, and other things that I would love to talk about at some other point. But this clinical team is really the core of who I am and what I do, and what drives, you know, many of my experiences and interactions with patients and research questions. So this is across the street at UC Davis in Sacramento, the Shriners Hospital. My lab is up on the sixth floor, and this is my lab team. Um, my siblings gave me this little neon sign, the Brain Fluids Lab, so I had to include that picture. But I'm very lucky to have Olga, my project scientist. So a lot of what I've been able to accomplish so far has been with a really, really talented project scientist that we can then co-run our lab, so I can focus on clinical things when I need to, and then she'll be able to cover the science aspects as well. I have a lab manager, four lab techs, and then an army of residents, med students, and undergrads who are all eager to contribute and be part of this fun set of endeavors. We have a lot of great collaborators. I won't be able to name all of them in this talk, but you'll recognize some of the faces. I didn't have room to put Pat in there, and Bonnie, and there's a whole other bunch of people that you know, the list goes on, and I hope to keep everyone in the loop. Um, you all know what hydrocephalus is, and I like to include this picture of what can happen to, you know, an infant when their skull is soft, and when they're having difficulty with managing their fluids early in life. It can lead to a pretty remarkable enlargement of the skull. And the treatment, as we've all talked about so far, is, you know, shunting, which is the most common treatment. This is highly prevalent all around the world. We are very fortunate in the Western countries to not be as prevalent, but it's still around 4,000 babies a year, which is similar to what we see in Down syndrome and cystic fibrosis. And we all know it's incredibly expensive, on the tune of $2 billion per year, just for pediatric care of these patients. And clinically, it's about 30% of my personal practice. And it's similar for many of the other pediatric neurosurgeons out there. So it's a huge part of our thinking and attention. So I want to start by talking about a case example of one type of pediatric hydrocephalus, and then to springboard into what the projects that I do and how they relate to this, you know, this type of a case. So imagine this is actually one of three triplets that I saw recently, and of the three, two of them actually had this problem, but they developed a small hemorrhage in a deep part of the brain, which is very common for preterm babies that only weigh about a pound. And you know, this hemorrhage was detected. You know, this child was 25 weeks gestation, so it was detected within the first week or two. The bleeding starts in one spot, and then it spills over to the back part. And you can see the blue parts. Those are the fluid parts of the brain, the ventricles, and the blood spills back there. Over time, then the ventricles start to enlarge. The blood starts to hopefully fade away and dissolve, but at some point it starts to compress the brain and cause the head to get larger. So at this time point, we typically have to decide on what to do treatment-wise. And the most common one, as I mentioned, is a shunt, and that often leads to you know, a decent recovery, with the caveat, of course, that shunts are not perfect. If only they were. And they most fail within the first 2 years, and almost all certainly fail within the first decade. There's many repeat surgeries, and then in addition to the burden of the original injury, which can cause issues with cognition, you also have the quality of life issues, which are often purely related to the shunt. But these are all at play. So I want to consider 3 neurosurgical questions, things that I, as a surgeon, have to think about at each of these stages. So the first question is, when we have a preterm infant with a hemorrhage like that, what do we do about it? Do we just sit and watch it, as I've been taught to do when I was a trainee? And is that what most of us do? Or do we try to be proactive and actually try to remove the blood, which is slightly risky in a 1-pound baby, but there could be some benefits. Some clinical trials have shown that children may not see a benefit in terms of shunting, but they may have better cognition if you get the blood out sooner. So that's a whole area of debate, discussion all around our country. It's being led mostly in Europe, but I've actually done a few cases of this, one of the first few in actually our region. So that's an active debate, and I have a whole subsection of the lab devoted to that question alone, taking human CSF, human neurons from various sources, and trying to ask the question of whether the blood removal will help with the brain function at that point. So I don't have time to talk about that right now, but that's a whole area of excitement in the lab. The area that I will talk about now is actually about what to do after we've already waited long enough that there is inflammation and there's blockage of the fluid and we have real hydrocephalus. Can we reverse it? Can we undo some of that process by trying to target the molecular features of it and use tissue in the brain to kind of counteract that? And that's where we can leverage ideas like exciting cell and gene therapies to do such work. And the last topic that my lab and my neurosurgical focus draws me towards is the question of whether we can do anything to predict or come up with better diagnostics to know if our shunt is going to work in which directions. And this then now transitions towards where Peter, took off, which is, we need better tools. But on that front, I have a couple people in my lab who are laser focused on a novel approach to measure pressure in different compartments. So we've got some interesting preliminary data on that too. So I'll pause on that, but to move on to the main question, which is, how can we undo some of the damage once it's underway? And that relates to the Innovator Award that thankfully you have all generously funded for my project and for my team. So this is an ultrasound image looking just above the eyes through the brain, but it's of my own son. He was almost 5 months gestation at this point. My wife is very pregnant. We wanted to just make sure everything's okay. Thankfully, he was. This all checked out. But I'll just walk you through some interesting elements of the images. I don't know if you can see my cursor, but the white areas around are the bone, and those kind of bounce those sonogram waves pretty well. The brain is gray or dark in between, and then you see these 2 very large blobs here. And some of you may have no idea what this is, and some of you may think, is that a hemorrhage? Is that blood? And some of you actually might get the right answer, which is that's normal. We actually see normal choroid plexus, this very strange, mysterious tissue in the middle of the brain that secretes a lot of the CSF and the fluid in the brain, but it is massive early in life. And it looks really tiny when you're an adult, but this is actually how important it is early in life. It is almost bigger than the brain and is responsible for communicating and secreting all the good factors. So thankfully, my son is doing well right now. But when not knowing what I just told you, you might think, goodness me, what is that? So this is what the choroid plexus looks like in a human. It has this very frond-like shape, branching, and it can get quite thick and big, as you saw in that picture. And if you take a little slice of it, one of these little fronds, you can see that there's an outer layer of cells, which are then shown here on the right side, that kind of line the internal tissue, which has a lot of blood vessels in it. It's very vascular. So every time your heart beats, it rushes and fills the blood inside the choroid plexus, and then there's some exchange that happens. So this is actually an image from my lab. We had a very nice technique to both stain the colors of this choroid plexus and take a nice clean image of it. And this is actually coming from a real human sample and source. So that's the real deal. And you see how it matches the image, the schematic pretty well. You see these line cells. The white is the outer side, and that's the part that exchanges and sends material out into the CSF, the brain fluid space. And in the ultrasound, you can see that's kind of an example of where this is happening. We're just kind of zoomed in. So this is the reality of what that tissue is doing and how it plays. And then in my postdoc experience with Maria Lettinen, who you've also generously funded and know quite well, we developed this idea that blood, when it is out there in the CSF where it shouldn't be, when those blood cells pop, they release a lot of potassium. And there's this very important ion channel transporter called NKCC1, this purplish, bluish colored transporter there with the arrow pointed down. And that's what shuttles a lot of the potassium in or out, usually out. But in the context of a disease, it might be shuttling mostly inward, and with that, pulling some of the fluid in. So the choroid plexus in that situation of bleeding might actually have a role of trying to counteract the problem. So here's a picture of one of the fronds of the choroid plexus, again, imaged in my lab from a human source. And you can see it's more of a 3D shape. You can see the surface areas. But what's unique about this is that the white-looking cells are a subset of the outer layer of cells that have been given a special gene therapy. So a virus was injected into that fluid space around it. And those cells took up the virus and happily started to express one of the genes that it provided. And that's why we can visualize it and see that they're white there. And if you zoom in and take a finer cut, so it's not 3D anymore, it's kind of a little slice, you can see which cells have that gene therapy and which don't. This is all with human tissue that I'm showing you so far, but now I'm going to show you some mouse data that's already been published during my postdoc time. The gray dots are mice that had hemorrhage injections, and those gray dots represent very high levels of potassium, as you can see on the scale to the left. And on the scale to the right, the purple squares represent those mice that had this similar gene therapy, but where they received more of that purple transporter to get more of the potassium out. And so those mice in purple then were able to have more normal potassium levels in their brain and also shrink down the fluid spaces. So we're kind of treating the problem after the fact. And as more evidence towards this, when we took these mice and put them under MRI surveillance, every line there represents a single mouse. So the purple lines are mice that were given a hemorrhage, but then got the gene therapy, and then their volumes came back down as a response. Whereas the gray lines are 4 mice who got the false gene therapy, and their brain volumes stayed up high after the hemorrhage. So this is very exciting and promising to us, but I don't like taking any information from a small animal and jumping straight to human work. So the first step was to do this in mice, which is the schematic represents what we did. We did these blood injections into small baby mice to represent the pediatric condition at P4, which is just 4 days after birth in a mouse. But then we moved on to large animals and human specimens in my lab here at UC Davis. I don't have time to talk about this in much more detail. This grant was focused more on human tissue, but just to let you guys know that we've done a number of pig surgeries now to replicate this model from mouse to do in pig. And as you see on the right, there's an MRI where there's a lot of white fluid space in the brain. This is a pig who got the blood injection only days after birth with blood, and then their brain fluid space is filled up. And this is a preliminary quantification of what that looks like over time. So if you follow them over 21 days, one of them had to be euthanized because they couldn't make it the full time. But in several of these pigs, we're seeing some very nice responses that match what we did in mice. But the point of this, lab experience was to transition towards humans. So along this roadmap I have here, we go from small animal to large animal, then to human specimens. And this is where your generous funding has really kickstarted the lab. Early when I started on, there's not a whole lot to draw from, but you guys really came in to help with this. So we're able to acquire human tissue from different sources. And some of it comes from adults who have brain tumors, and they might be dangerously close to the choroid. We can get a sample that way. Some are from fetal terminations, and some are, potentially coming from stem cell sources, which I haven't quite explored yet. But these samples then, give us a sense for what is happening with the actual human tissue, and can we perform a gene therapy like you saw in the mouse and like we're going to try in the pig, but can we actually do this in humans for real before taking this to the FDA and towards a clinical trial? And so that's where I want to guide you guys on this in this little adventure here. So if you take that human tissue, we can magnify it the way you see there, and we can then add the virus to its surrounding while it's still alive. And so this living choroid plexus in a dish can take up the virus, and we can see where it gets infected and how it can deliver the gene we expect it to deliver, and then how the cord plexus can then use that gene to make a change in the environment around it. And if I keep zooming in, you can see then a similar image to what I showed you earlier. That's how magnified you get from the very large cord plexus, almost like you saw in my son's ultrasound, to the actual physical piece of tissue, then to the microscopic image. And this is again preliminary data, but generated with funds that you've provided. But we've been able to now do this experiment and do all the imaging and have my technician go through all the samples and do the quantifications, but then to ask which virus should we use. And I hope to publish this data in the coming year. But this is then going to hopefully guide the future human clinical translation in choosing the correct virus, the correct dose, the correct means of delivering it. And this could hopefully be used not just for one type of hydrocephalus, but in theory to treat other types of hydrocephalus once we get the technology down. So that's one half of the aim of this grant, was to use human neurosurgical specimens for gene therapy research. But then the other aspect of it is to ask questions related to what is going on physiologically. How does that bit of tissue in the middle of the brain change its environment around it once hemorrhage has touched it? So I'll go back to my son's ultrasound. So here's his cord plexus in bright white. And if he were to have a hemorrhage, we don't quite understand what happens to this tissue. We've studied it in mice and rats, but it's not quite clear what the connection is to humans. So I'll first show you some mouse experiments. So this is cord plexus from a mouse. And when you take it out and then splash some blood on it, you can see some wild activity. Every dot there is a single cell, like I showed you before in that lining of the cord plexus, and they get very excited when there's blood around them, which means that they're doing things inside. They're changing their normal state. The blood alters their physiology, and we don't fully understand what that is doing. I did the same experiment on a mouse where we're now looking inside a living mouse, a mouse who's actually awake, running on a wheel, and we have a little window in his head. And we were able to inject blood and then image the same finding, which is very exciting. So this holds up not just as a outside the brain, but actually in a living animal. And these two little videos here show what the cells look like when they get a lot of excitement. The red dot there is the nucleus of an epithelial cell, and those green little explosions are the outer membranes of that green cell now bursting new proteins into that fluid space. It's wild, and we can induce that in different ways. And that's all in a mouse. Now, for the first time, we've been able to try that experiment with living human tissue. And here's a human cord plexus that then was exposed to some of the same stimuli you saw in the mouse. And they start to do astonishingly the same thing. They start to bleb out and push out proteins into that surrounding fluid space, thus modifying the CSF around them, and thus potentially modifying how your brain reacts to it and how your cognition may fare after an insult like that. So that's going to be all hopefully published within the next couple months in a joint author work with Maria Letnin's group. And there's Courtney et al. Showing the bars showing that there's an increase in protein that's secreted from mouse cord plexus when they get this stimulus, but we see a similar response with human too. Then rather than take human samples from babies who have hydrocephalus and ask, how does this baby's CSF compare to that other baby versus that other one over there versus the one that didn't get any hemorrhage? It's hard to compare different humans. They all have very different brain fluid environments. But now imagine you had the same cord plexus, this kind of red membrane that I'm showing you here, and I was able to cut it in half. And I take half of it and treat it like nothing happened, just a normal day. And the other half, I'm sorry, but we're giving you a hemorrhage. Now, for the first time, we can have a perfectly well-controlled compare side by side in the same human tissue what's going on and get unprecedented level of scientific detail about the exact types of proteins, and at an omics level approach. And to do that, this is where a lot of your funding has come in, is actually doing some of these very experiments with some of these samples of cord plexus that I have to look at their protein responses. And I've enlisted some friends, colleagues, and other award winners from prior and active Innovator Awards to actually help out with this process. They're interested in similar pathways. And I'll point out Dr. Isaac Alberts there in the middle, because he's actually helping with a lot of the omics type analysis. When I'm getting a lot of data on what proteins are coming out after hemorrhage in this perfectly controlled experiment, and he's going to try to help me out and figure out what is meaningful, what's real, and we'll carry that forward. So this is an example of the different things that we're doing in my lab. utilizing this Innovator Award and utilizing human specimens and trying to really step away from just looking at animal models and try to put it all together. And so, in the last few minutes that I have, I want to also talk about, broadly an opportunity that I had in recent workshops that the HA had hosted to think through what are our priorities and how can we, as the community of surgeons and other clinicians and scientists and patients and families, what are our priorities? Can we have a workshop to talk about this? And so, a lot of things that came up were non-invasive treatments, of course. And so, these conferences happened over a span, within a year of time, in two different cities. And we came up with these three broad themes as to what we thought would be important for all the workshop attendees. So mechanisms of CSF pathology and physiology, leveraging big data to identify new targets that could be used for new therapies, and then to design our preclinical studies in mice or pigs, what have you, but with a laser-focused translational intention to pick the right criteria that might be meaningful for a real human trial. And so these three elements are now out in a paper that's published with all the authors you see there. Happy to be a part of that team and to see some of you here. And I hope that you get the sense that some of the work that's now influencing my own career right now is related to these three themes. We're looking at pathophysiology with human tissue. I'm going to be leveraging big data in terms of what proteins are out there in the responses. And I'm designing some of my preclinical studies with all the things in mind to try to make sure we have the most potent, non-invasive future therapy, which hopefully may be something along the lines of gene therapy or something along the lines of, who knows. But I'm happy to be part of this community and to help drive this process forward. So thank you so much for your attention.
Thank you, Dr. Sadegh. That's amazing. Are there questions, Linda, that are in the Q&A for Cameron?
We have not had any show up yet, no.
Is there anyone that is on the call that would like to go off mute and ask a question? I mean, Pat McAllister's on this call. You always have a question.
I was going to show you the pig data soon, so preview.
That's exactly why I'm trying to stay muted, because I talk too much. I want to hear what other people have to say.
I'm not seeing any raised hands, but if you do have a question, you can certainly come off mute and ask it.
All right.
Okay, you guys, this silence is killing me.
I actually have a question. I got in a few minutes late because I just got home. I was just curious because I'm not sure what I missed coming in. Like who, with the research and what you were talking about, I did see something that was pediatric related when I got in on the call. Like, is there anybody with what you were discussing, like that this may not benefit, or is there hope that this could benefit like anybody in the future with this condition?
Yeah, it's with the way scientists do things, they often pick really nitty-gritty problems to make an example of something before they broaden it out. And this is one of those examples where I'm focusing on one type of hydrocephalus, one of the many etiologies, but I really hope that it can be expanded to the other types. As an example, some adults, of course, can get hydrocephalus from hemorrhages. So hemorrhage doesn't necessarily have to be about the age in this case. And then there's other conditions where you can have inflammation. So it doesn't necessarily have to be a hemorrhage per se. It could be maybe an infectious etiology or some other injury. Some people will have it after trauma or stroke or certain types of tumors. So I do see a lot of potential in broadening it. And I have to sort of hold myself back when I speak to scientific communities because you don't want to spread yourself too far out, create vulnerabilities for criticism. So usually it's better that we focus ourselves on one narrow part of it. But yes, I have major hopes for expanding this to other types of hydrocephalus.
Thank you.
All right, Dr. McAllister.
But wait,
Well,
I have a question before Pat.
No.
All right, who's that?
Oh, it's
Kelsey
gross.
Oh, gross. You go for it, Paul.
So you mentioned something in the whole process that was about an ion channel moving potassium, and I was very curious. Was that a basic science discovery that was made in the lab you were working in at the time, or was that someone else's discovery that got applied to your work?
Both, both. There's been a lot of interest in the transporter I mentioned. The name NKCC1 has been cited for all sorts of different scientific works, not just in the choroid plexus, but in neuronal function, how neurons can regulate some of their cell size. It's highly important in the kidneys. So for anyone who has hypertension and is taking a diuretic, some of the drugs you take are actually targeting that same transporter. It just happens to be also expressed in the renal tubular cells in the kidney. So that potassium transport has been studied by many other labs. It's also been brought to prominence by some of the ones that you guys have funded and have been supportive of. So Chris Colley's group has been studying it quite keenly as well. Other groups, and then in Maria Letnin's lab, it also came as another candidate and target because at the time I was there, a couple of her lab members were looking at the developmental trajectory of these different transporters, which wasn't really understood at the time. We know they're there in the adults, but when do they start to become important in a baby? And so with baby mice, we start to look at their expression levels, and NKCC1 also popped up high on the lists independently for that reason. Had a very rapid ramp up compared to some of the other ion transporters. And the initial tests we had done on NKCC1 were actually in that developmental context, even before the hemorrhage model. So it's something that happened amazingly with synergistically and in parallel to the work that I started. I started to bring in more of the neurosurgeon's perspective on hemorrhage and measuring compliance and other physical parameters of the brain and so forth. But you're right, a lot of this draws from multiple other sources. It wasn't a single brand new discovery, but we're trying to build on that with all the work I just showed you.
Great. Fascinating work. Thanks.
Well, thank you.
Okay. I have a comment and I have a question.
hmm
I want to lead with a comment. The I know that these are troubling times with grant funding. Diana did a really good job of explaining that. There are a lot of unknowns. And I, number one, want to congratulate um, everybody at HA for doing a lot. You have to lobby your Congress people. I'm writing letters, I'm making phone calls, and everybody on this call should do the same thing. But I want everybody to know that the scientific community, especially the investigators that know HA, we all know each other. We are not giving up. We have banded together. If nothing else, we've started calling each other. We're forming groups. We're trying to work collaboratively in a team, um, and work on particular aspects. And I'm really encouraged about that. It's real easy to get depressed and suck your thumb and go away, but the investigators that we all know are not giving up. So that's my comment. Um, Cam, that was a great talk, and that is really fantastic work. What I hear a lot when I talk to patients is how long is it going to take these non-surgical therapies to get into clinical practice? So you're in a perfect position. You know how long it takes to do the science. You know how long it takes to get it through the FDA and all that. And what are your thoughts about how long it takes and what you have to do?
Well, I think you probably have more experience and knowledge on that than I do, but I'm happy to take a bite at
Oh,
that. The simple answer is it takes a while because especially if you work through a large animal, because they are just harder to come around. There's fewer centers in the country that can do that type of work, and they're expensive. Um, but they're also highly valuable. Any hydrocephalus treatment has to deal with the issue of the brain fluid volumes. That's the most important factor here. We're dealing with real physical amounts of fluid. A can of Coke every day of fluid is coming out of your head, one way or another. And when you're talking about that kind of volume, a mouse experiment seems like a joke sometimes, right? So we kind of deal with this. They're very important and useful in different ways. But so then if you think about large animal work, it's devastatingly hard. And if that's the requirement you have to get into the human clinical trial, it takes time. But it's time well spent and worthwhile, because if it works on an animal that's within a scale of 10 to a human, I will offer that to my child. I'll take that therapy myself. There's no question. So I think raising the bar to that height comes with advantages and disadvantages. So if it works on this pig, I'll have full confidence to try it in people. But on the other hand, it's going to take longer, right? It's going to take, a few more years. And the FDA process is not kind either in that sense. So it will add time. So yeah, I think it is what it is. And, we're just doing our best here, and we'll keep pushing forward. But I've spoken to at least one consulting company that would help with investigational new drug applications, and their consultation said that we have great success with this, but it also takes time. You need independent laboratories to verify what you've done. So even after I've done my work, someone else has to repeat my work in a primate or another monkey in their own lab where I cannot control anything. So imagine that takes another couple of years, and then starting a clinical trial also a couple of years. And we have one trial at UC Davis, which is probably the most uh, emblematic of how this can be done. And this is by Diana Farmer, who's implanting stem cells into spina bifida patients to see if that will help with their motor recovery in the womb. And imagine how long that took. She started with research on sheep models of stem cell implantations where they had a model of spina bifida. They're putting the stem cells on there. And that was 15 years ago. And now I am also part of this. I'm actually physically putting stem cell patches on fetuses in utero, closing the womb up, waiting a couple months, letting the baby marinate some more, and then they're born with a repaired back. And then we're trying to see if the stem cells are doing the work that we think they're doing. But that's an example of what can be done. And I take, you know, mentors like her also into account, like, hey, how can we get this going? So once I get good, strong pig data, I'm talking to Diana Farmer, I'm talking to all the friends I can to see how we can go from large animal model to California Institute of Regenerative Medicine funding on this tune of multi-millions of dollars to then getting this to an FDA phase 1. Like there's a process, and it'll take time, but I hope it'll be worth it at the end of it.
It definitely will be, and I should tell. Part of the reason we started to work on a pig model of hydrocephalus was we knew that the pig brain was very similar to a human brain, and in the course of the last 5 years, I have found out that the FDA loves pigs. It's a great large animal model. So I'm really glad that you've taken that. It's a big step. It's expensive, but it'll go a lot faster if you can show safety and efficacy in the pigs. So great job. Thank you.
Thank
you
you,
so
Pat.
much.
I just want to acknowledge that I'm impressed about how many of you are hanging with us. We've kept you a little bit long, but I hope it was worth it. It was for me to hear both of these inspiring presentations by Dr. Chiarelli and Dr. Sadegh. It's wonderful to see that we have neurosurgeons and scientists who actually want to help solve these problems to make hydrocephalus care better and more effective. So thank you, Cameron. We'll say thank you to Peter, even though he's off taking care of patients right now. But both of these presentations were incredibly inspiring, and I hope you all saw that as well. We want you to know that some of the research we're funding, we believe in. Their peers are reviewing this science before it gets funded, so we know there's excitement around the science that gets funded, and we just can't wait to see you be successful, Dr. Sadegh, and same with Dr. Chiarelli. But I want to also say about all of you on this call, we can't say enough about how important you are to the success of our mission. And you inspire us every day through your generosity to the Hydrocephalus Association. And I just hope this call helps to reinforce that your support is leading to impactful results, right? We're improving lives. And hopefully you see that the return on investment, a gift to the hydrocephalus, Association, your return on investment is really beyond compare. So I'm inspired. I hope you all are inspired. I have some announcements, but if you need to pop off, I will do them and they'll be on the recording. But we will also for sure make sure that everybody gets the recording, people that signed up and couldn't get the recording. And again, appreciate all of you for being here. So announcements if you want to hear them, or you can wait. We are always looking for ways to engage the community, and we have a new fundraiser called Games for Brains. So if you like to do gaming, video playing, get video games, or you like to have poker tournaments or play cards with your friends, this is a new way you can help raise money for the Hydrocephalus Association while having fun. If you're a runner, we also have bibs for the Marine Corps Marathon this year where you can run and raise some funds for us too. Our walks have opened. You can find a site nearest you and register. Some of you recall doing 100X Causes campaign where you get on your phone and give your opinion on different restaurants and stores, and that money helps us as well. My husband can't wait for this campaign to start. So he can do 75 opinions. No, we'll let you know more about it. They're quick surveys, but it really does help us out. So finally, we're always looking for volunteers. So if you're interested in getting more involved than you already are, please reach out to us. And thank you again to all of you. And have an incredibly wonderful evening. Appreciate you all.